Let's talk about lifecycle management with Helm. Now, lifecycle management can sound like a fancy technical term that's too abstract to understand at first glance. So let's translate it into plain English by taking a look at some practical examples. Now, each time we pull in a chart and install it, a release is created, as discussed in the previous lessons. A release is somewhat similar to an app, but more specifically, it represents a package or a collection of Kubernetes objects. Now, since Helm knows what Kubernetes objects belong to each release, it can do things like upgrades, downgrades, or uninstalls without touching objects that might belong to other releases. So each release can be managed independently, even if they're all based on the same chart. Now let's just create a new release and discuss this as we go along. So we'll install a pretty old version of this Nginx chart. By the way, you can pass in a specific version of Helm chart to install using the version option in the install command like this. We now have an Nginx release, plainly called Nginx release. And now imagine 2 months go by, which is a long time for any piece of software, but especially for a website. A lot of security vulnerabilities get discovered and they need to be patched up. Now, our Nginx hosted website may have many objects in our Kubernetes cluster. When we upgrade the pods running Nginx, maybe we also need to make some changes to other Kubernetes objects. For example, the newer version of Nginx may require a new environment variable to be set or new secret to be created, which requires changing configuration objects and other files part of the manifest files. But it may be hard to keep track of all pieces that need to be changed. Fortunately, as we said, Helm keeps track of everything associated with a release. So we don't have to upgrade our objects one by one. Helm can automatically upgrade them all with one single command. But first, let's see what version of Nginx is running in our pod. We initially have to find out the name of our Nginx pod. So we run the kubectl get pods command to see the pod that we created. Then we run a kubectl describe pod command to see more details about the image. And we see that it's running Nginx version 1.19.2. So that's pretty old. Now let's see a Helm upgrade in action. The command is rather simple. So we just tell Helm what release we want to upgrade and then specify the chart that this release is based on. So we now run the Helm upgrade command to upgrade the Nginx release. So revision 1 is now replaced by revision 2. Note the revision number in the output of the Helm upgrade command. So did the Helm upgrade command really do its job? Let's check. In the upgrade process, the old pod gets destroyed and a new one gets created. So we'll need to get the name of the new one. So we follow the same Helm process again and get the new pod name. Then run a describe on it, and we see the new version, which is Nginx 1.21.4. So there you have it. We just went through the so-called lifecycle management with Helm. A release can exist for months or years, and Helm can manage its lifecycle in many ways by keeping track of its current state, previous states, and bring it into future states. So in this case, we brought the release into a future state by upgrading it. But Helm kept a record of the previous state too. We noticed the revision number changing to 2. So the previous state would be revision 1. Now, how does that help us? Let's take a look at our releases. Run the Helm list command to list the current releases. And we have our Nginx release listed. We see the current revision number, which happens to be 2. In this case, we know what the previous revision was and what the current one is. But say we work in a big team and lots of people manage their releases, this output doesn't really tell us what happened. So how do we dig deeper? Run the Helm history command to see more details about a particular release. This is a lot more helpful. We can clearly see a lot of useful things. What chart version was or is used in each revision, what app version was or is used in each revision, what action actually created that revision. Was it an install, an upgrade, or a rollback? So this paints a clear picture of the stages our release went through, its lifecycle history. Now let's assume this upgrade did something that we don't like. Helm's lifecycle management allows for another cool thing called rollback. Now this lets us return a release to a previous state. So in this case, we want to return to revision 1. So in this case, we run the command helm rollback nginx release and specify the revision number that we want to roll back to, and that is revision 1. Now, when you do that, remember, Helm reverts all configuration to how it was previously in revision 1, but technically it does not go back to revision 1. Instead, it creates a new revision, revision 3, with a similar configuration as in revision 1. So if you list Helm revisions with the Helm history command, now you will see that there are 3 versions, with revision 1 and 2 having the same chart and the app versions, and there is a note in description that says it's a rollback to revision 1. It's worth mentioning that we chose nginx here as it's simple to upgrade, but there will be Kubernetes packages that may require a few extra steps to upgrade. For example, if we have tried to upgrade the previous WordPress release that we created, we would have got this output. Now, that's not to say that this is a problem. It can be easily solved by adding some more parameters to the command line as instructed in the text, but why does this happen? In this case, Helm cannot upgrade everything without having access to some administrative passwords. It needs administrative access to the database and to the WordPress website itself so that it can get permissions to make necessary changes. It's also worth mentioning that although rollbacks are very similar to a backup restore feature, it doesn't cover file or directory data that may be created by our applications. Instead, Helm backs up and restores the declarations or manifest files of our Kubernetes objects. So for things that use persistent volumes or other forms of persistent data, or something that is external, maybe like an external database, a rollback won't restore that data too. For example, imagine you roll back a MySQL database server. The MySQL pods will be restored to their previous states, software versions used, and so on. But the actual database, its data, will remain the same. Its data is not going to be backed up or restored. So there are options available to take consistent backups of databases before upgrading charts, or even to roll back or restore databases, but they're done using what is known as chart hooks, which we will discuss later in this course. Well, that's all for now. Head over to the labs and get some hands-on practice. Let's start with writing our own Helm charts first. Helm charts are incredibly versatile, and they can automate almost any kind of Kubernetes package installation that we can think of. In a way, they're similar to installation wizards on operating systems. An installation wizard Besides extracting the application files and directories, can also add relevant shortcuts to the desktop, configure the application to launch when the operating system starts up, install additional libraries that are needed, and so on. The same is true for Helm charts. Although charts are technically not programs, they can act like programs. Besides just installing various Kubernetes objects to get our app up and running, they can do some extra stuff too. For example, we can write the chart in such a way that whenever we do a Helm upgrade, a database can be automatically backed up before that happens. So we have a way to restore data from backup in case something goes wrong. And that's just one small example. We will look at those kind of complex setups with hooks and everything towards the end of this section. It can be overwhelming to think about like a million things a chart can do at this point. So let's start with something simple and learn the important bits and pieces one by one. So let's start by looking at how to create a Helm chart from scratch. Let's use the example of a simple Hello World application. We have a deployment with the Nginx image with 2 replicas, and we have a service to expose this application. Super simple. Let's see how we can create a Helm chart from this. Earlier, we learned that Helm chart is a directory with a specific structure. With the templates directory and the other supporting files like the values.yaml, the chart.yaml, license, readme, etc. So our goal is to create a directory structure first, something like this. But you don't have to do that yourself manually. You could run the helm create command and specify a chart name to create a chart structure. And this creates a skeleton structure of a Helm chart. So now you just have to go in and modify these files or add the relevant files to the templates or charts directory. Now you'll see the chart.yaml file already has some sample data in it. It has the name already set to Nginx chart because that's what we gave in the command line, and a sample description and some sample values for versions and app versions. Now let's assume the following scenario. Let's assume that we are building this for our company and we want other employees or other users that use it to have some basic information about the chart. So we'll modify the description and add an email at the end under the maintenance section so people can contact us if they have any questions. And feel free to modify the other details and add other properties to it, such as the home, the URL to the home directory, or a path to the icon, etc. As required. Next is the templates directory. It already has some files that are samples. And these are samples automatically created by Helm create command. For now, we will just get rid of these and just work with the files that we already have for our application because our requirement is pretty simple and straightforward. Okay, so we now have an empty templates directory. And our first goal is to move the files that we already have for our application, the deployment file and the service YAML file, into this directory. And to be honest, this should be it. Once we place the relevant files in the templates directory, our Helm chart technically should be ready to go. Our chart is now ready to be installed using the Helm install command. However, note that these files in the templates folder have all static values in it. For example, if you look at the name of the deployment or the number of replicas or the name of containers, they're all statically defined to hello world, for example. Now, what could be the problem with that? Imagine we install the Helm chart with this using the Helm install command. We give the release a name, hello world 1, and point to the Nginx chart directory that we just created. It installs the chart and creates a deployment. The deployment is named hello world. This is because the template file has name hello world defined in it. Now, what happens when you try to install another release of the same chart? It fails with the error message that says a deployment with the name hello world already exists. And of course, as you can see, this is because the deployment name is static, is defined statically in the deployment.yaml file. And every time that we are installing a new release using the Helm install command, It's simply trying to create the same deployment with the same name. So it must have different names each time you install a Helm chart. So how do we solve this? We templatize the name of the deployment. We use Helm's templating language to basically tell Helm that the name of this deployment should be based on how the user chose to name his or her release. So release.name becomes hello world-1, and the name of the deployment becomes hello world1-nginx. So let's take a closer look at that template. Now we templatize something by adding something between the two curly brackets. This is called as the template directive, and it's not something very specific to Helm. It is in fact the Go template language, the Go programming language's template language. Within the curly brackets is where we specify the path to the objects that we'd like to access. It starts with a dot. The dot refers to the root level or top level scope. We'll talk more about scopes in the upcoming lectures. The release.name in this case is the release name that we have specified in the Helm install command. So when we run the Helm install command, the template directive is replaced by the release name to form hello-world-1-nginx. So that's how templating works. Now, similar to release name, there are other objects as well, such as release.name, release.namespace, release.aceUpgrade, revision, service, etc. Or you can refer to any values from the chart.yaml file that we created, such as the chart name itself, or the API version that we've defined in the chart.yaml file, or the version or type, keywords, home, etc. Or even details of the Kubernetes cluster itself with the capabilities object, such as the kube version, or the set of versions of resources available on the cluster, or the Helm version and such. And anything that starts with the values is something that refers to the properties defined in the values.yaml file. And this could be any number of values defined in the values.yaml file, and currently there are 2. Now, one other thing to note here is the difference in case convention. For the first 3 objects, release, chart, and capabilities, the second part after the dot all starts with a capital letter, such as name, namespace, AceUpgrade, and others. However, if you look at values, you'll see they start with a small case. So why is that? These are case sensitive, so it is important to be careful with the case you use. The first 3 are built-in objects, and as such, they must follow the capital letter naming convention. Everything under values are user-defined. That is, whatever user defines in the values.yaml file. So the users are free to follow whatever naming convention that they'd like to follow in the values.yaml file. In this case, these values follow a small case letter. And so you must use whatever it is that is defined in the values.yaml file. Coming back to our example, if we create a release called Hello World 1 and another called Hello World 2, the first one will name the deployment Hello World 1 Nginx, while the second one will call it Hello World 2 Nginx. And we now have guaranteed unique names. Now remember to do the same for the services or any other objects that you create as part of your Helm chart. We should follow similar techniques for all Kubernetes objects that must have unique values or names. Helm does not allow us to install 2 releases with the same name. So by basing the names of our Kubernetes objects on the release name, we can be sure that our charts can never create 2 objects with the same name. Furthermore, when we later explore our objects, seeing something called release 5-pvc or something will quickly help us identify to which release this object belongs to. So whatever value you think shouldn't be hard-coded should be templatized. In this case, the replicas and image names could be values that we need to allow the user using our charts to customize. So we can templatize them by using the values.replica count and values.image template directive like this. So anything defined as values should either be passed through the values option or the set option while installing Helm chart, or be defined in the values.yaml file like this. So let's take a closer look at the value defined for image. Since it's text, we could access it within the deployment.yaml file as values.image. Now, image could have an image name and a version number, as well as other properties such as pull policy, etc. So we can either write it as image underscore repository, image underscore pull policy, or image underscore tag. But a better way and the right way to do it is to write it as a dictionary like this. This way, we can refer to the image name as values.image.repository. So values tells the value is from the values.yaml file. The image is the image dictionary within the values.yaml file. And a repository is the name of the repository within the image dictionary. So that's how the template directive is formed when we work with dictionaries. And if we want to add the tag on, then we add the tag using the same format, values.image.tag, like this. So the image repository part becomes Nginx, and the image tag part becomes 1.16.0, and together they form the complete value with the colon in between. Well, that's how you define a dictionary in the values file and use it in a template. So to summarize, when we install a Helm chart, Helm uses the files in the templates directory and then combines it with the information about the releases, such as the release name and any other information, the data stored in the values.yaml file, and the chart details to form the final versions of manifest files as seen here on the right to deploy resources on Kubernetes. Now, apart from these, it also refers to any other object that are available, such as the Kubernetes cluster itself. So there may be some data that is pulled from the Kubernetes cluster itself, and any other objects that is available to be used in a Helm template. Well, that's all for this lecture, and I will see you in the next one. Now that we have developed our first chart, let's make sure the chart is working as intended. Now, there are 3 ways to verify your Helm charts before installing them. Linting helps us verify